Hi y'all, here's another function example. This time we're going to work with a rational function. So we're starting right off with the rule. The rule is that g of y is equal to 3y divided by y plus 4. So whenever we see g of something, we know that we need to refer back to this rule. And this function is always going to build a fraction, and in the top of the fraction it will put 3 times our input, and in the bottom of the fraction it will put our input plus 4. So every single time that's what's going to happen if we take g of something. Okay, so let's start off with find g of 0. Okay, so g of 0, we're inputting 0 into function g. We refer back up to the rule for function g. The rule for function g is that we should build a fraction, and the top of a fraction we should put 3 times our input. So 3 times 0 is 0. In the bottom of the fraction we should put our input plus 4. So 0 plus 4 is 4. 0 divided by 4 is 0. Remember, if you have 0 in the bottom of your fraction, the fraction is undefined. We can't divide something into 0 groups, but if you have 0 in the top of your fraction, you get 0. Okay, let's try a little bit messier one. Let's find g of 1/2. Okay, so we start off the same way. We're supposed to input a 1/2 into function g. So we're going to build a fraction. In the top of the fraction, we're going to put 3 times our input. So 3 times 1/2 is 3/2. It is 1.5. Given the choice, I would always choose to write it as an improper fraction, because if we need to do arithmetic after this, it's going to be much easier, and we will need to do arithmetic after this. In the bottom, I have 1/2 plus 4. And I'm just writing this out instead of doing it because I want to show you 2 different options. So one option is to go ahead and follow the order here. Fraction bars are like grouping symbols, so it basically puts parentheses. So we would first simplify in the parentheses, and then we would perform the division. So we would say 3/2 divided by 4.5, so that's 9/2. Okay, so first simplify in the group, and then perform the division. 3/2 divided by 9/2 is the same as 3/2 multiplied by 2/9. We can cancel the 2 out of that fraction, and we can also cancel a 3 out of that fraction. When you cancel, make sure you're really clear on the fact that that's a division. 2 divided by 2, which leaves 1. And then 3 divided by 9 leaves a 1/3. And when we multiply across, that's what we have, 1/3. Okay, so this is one option, and probably that's the way I would do this problem, but I want to show you a different way, because when there starts to get to be a lot of variable mess, it's nice to have sort of a shortcut for this. So another option is to take this, and I'm just going to rewrite what we had, and say, okay, I have fractions and fractions, and that is never ideal. That's one of the things you should always try to deal with, try and simplify. I would like to clear out the internal fractions. So I would like to make the 3/2 not be a fraction and the 1/2 not be a fraction. I can take advantage of the fact that I have this big fraction bar in the middle and say, okay, well, it's always legal to multiply by 1. If I do it in a sneaky way, it will simplify this nicely. So basically, I'd like to cancel the 2's out, which means if I multiply top and bottom of the big fraction by 2, on the top, I'm going to get 3/2 times 2. The 2's cancel nicely, and all I'm left with is the 3. On the bottom, really important that you realize there's a distribute here. I have a sum, which I'm then multiplying by 2, so I need to make sure that I multiply each of the terms by 2. The first one works out beautifully. 2 times 1/2 is 1. If you don't remember to multiply the 4, you're going to get this wrong. So 2 times 4 is 8, which means I have 3/9, otherwise known as 1/3. Okay, so I'm not claiming that the second way is necessarily better here, but when we get to some messy problems with fractions and variables floating around, it can be really efficient. It can work through simplifying this thing a lot more quickly than performing the addition or subtraction followed by the division. So keep that one in mind. That's a really good one. We'll use that a lot this quarter, and we use that a lot in calculus as well. All right, let's try g of -4. Okay, so g of -4, we should be referring back to the rule for function g, which is create a fraction bar. On the top of a fraction, put 3 times your input, so 3 times -4 is -12. On the bottom of the fraction, put your input plus 4. -4 plus 4 is 0. And here's what I was talking about earlier. We cannot divide something by 0, so this should be an undefined. The function is not defined for an input of -4. I would also take it does not exist. G of -4 does not exist. I would take -4 is not in the domain of G, so I'm going to use undefined as my default. There are a couple of variations on this that would be fine, but do be thoughtful. If you say no solution here, you're wrong because I didn't ask you to solve anything. No solution is stating that there is not a solution to the equation I started with, and if I didn't start with an equation, then I am lying. Okay, so let's see if I want anything else about that one. Oh, I think I do, actually. So what we've just discovered here is a domain problem, and we're going to talk about domain based on looking at a function defined by a formula in this section as well. So let's go ahead and mention it here. For fractions, we need to be a little careful. We don't want to have that division by 0. So this one right here, I can't plug in -4, but really I can plug in anything else I want. Performing division, the only way you can get in trouble is with that 0 in the bottom, and -4 is the only thing that would give you that 0 in the bottom. The multiplication, the addition, there's nothing you can't multiply by 3 or add 4 to. So really the domain of this function is all real numbers except -4. And you can write that out for me if you want. Squeeze it in here. Some of the more formal notations would be if you want to do your set notation, the set of all y such that y does not equal 4. This is actually, I think, the short version. And again, I'm not super picky about the set notation part of this, so if you just want to write down y does not equal 4, that will be okay with me. I'll understand what you're saying, but I want to make sure you understand what you're saying. If you just write down y does not equal 4, you mean all real numbers but y equals 4. So what we wrote up above can be written this way. You need to be clear that that means everything else is in the domain. So if you don't want everything else in the domain, you need to write down more restrictions. If you want to do this one in interval notation, this is actually the one time where I think it's a little bit more complicated. We want everything except for -4. I've been saying it, but it's not negative up there. So let's go from -infinity to -4. And then we want to exclude -4, but we want everything bigger than -4 as well. So this is how it would look. It's really important that you're clear on this. We don't want to stop at -5 and start again at -3, for example, because that's assuming that the variable can only take on integer values, and that's not true. We're talking about real numbers. So -4.1, -4.01, -3.99999, all of those should be included. It's only the single value -4 that we leave out, and this is how we would show it. Round brackets leave out the -4. Otherwise, we've got absolutely everything else. Okay. Let's get a little messier. Let's get some variables involved. Let's try to find g of y plus 2. Okay, so again, as soon as you see something like this, you should be asking yourself, where's function g? What rule does it follow? Function g is still sitting up here at the top, so we're still following the rule. 3 times our input divided by our input plus 4. Parentheses, again, we don't actually need them on the bottom, but we do on the top. So if in doubt, throw parentheses around your input. It is never wrong to put parentheses around your input, but it can be wrong to leave them off. So again, great example here. If you don't include the parentheses on the bottom, you'll be just fine. You don't need parentheses to sort out the order of the addition. Addition can happen in whatever order and you'll get the same result. You do need the parentheses in the top. If you don't include them, that says we're multiplying the y by 3, but not the 2, and that is wrong. We're supposed to be multiplying the entire thing by 3. We should do some simplification here, so let's go ahead on the top and distribute If you don't want to distribute here, I'm actually fine with that. As it's written, the top is in a factored form, so the big operation is the multiplication, which means we'll have the opportunity to cancel later if we leave it in this form. So completely okay if you want to leave the top, but I'm going to go for it. The bottom is not in a factored form. We have parentheses, but this is not attaching two things that are multiplied together. This is attaching two things that are added together. So we really end up with a y plus 6 in the bottom. And you want to be clear in both of these steps that there's no cancellation you can do. In the top step, some people want to cancel the y plus 2, and that's wrong for the reason I just said. Yes, y plus 2 is a factor of the top. This is a product, but it is not a factor of the bottom. The bottom is a sum, so we can't cancel something out of a sum using division. And when we do this cross through y plus 2 over y plus 2 is 1, that's a division. Same thing here. Now the top and bottom are both written as sums, so we shouldn't be canceling any individual part. You could cancel the entire y plus 6, but in the top, y plus 6 is not a factor. The 6 is not a factor of the top or bottom. The y is not a factor of the top or bottom. So canceling 6's would be bad because they're not attached by multiplication, which means we can't divide them out. Same thing for y's. Same thing in the top for y plus 6. This plus in the middle messes it up. So make sure you have factors before you try and cancel. So we're done with g of y plus 2. Okay, let's compare that to g of y, the plus 2 outside the parentheses. So this is a really important difference for you to start paying attention to. This is going to be an especially big deal when we're doing some of our graphing later. We need to identify when we're messing with the input versus the output of a function. So what we just did up above was input of y plus 2. So we changed our previous input of y by adding 2 to it, and we get a new output. This is not saying to add 2 to your input. This is saying to add 2 to your output. So this says plug y into g. When we plug y into g, we get 3 times y over y plus 4. And then we're supposed to add 2 to our output. And I don't need you to do anything else with that. You can get a common denominator if you'd like to, but I'm completely fine with this. There's no motivation right now for me to say that adding that together is better than leaving it as is. So it's just fine. If you want to get a common denominator, that's not wrong, but it is not necessary either. So input versus output, really, really important. Start to really try and pay attention to that and say it to yourself that way. Okay, let's see if we can sneak one more on the page before I run out of room, at least the beginnings of it. Let's try, find g of 2 over y. So again, getting fractions involved in a function that already contains fractions tends to create some algebra mess for us that's really good practice. So g of 2 over y, this says follow the rule defined by function g, which is build a fraction. On the top of the fraction, you're going to have 3 times your input. 3 times 2 over y is 6 over y. You want to be really careful. In fact, I think I'm even going to make a side note here. I was trying to figure out 3 times 2 over y. When you're doing that multiplication, move up so you can see here. The 3 is not a 3 over 3, it's a 3 over 1. So you multiply the top by 3, you do not multiply the bottom by 3. I actually get a lot of mistakes right there, so make sure you're really careful about that. Write the step out if need be, don't skip it. All right, and then the bottom of my fraction is supposed to be my input, which is a 2 over y plus 4. And here again, we have options on simplification. Order of operations says that we have to perform the addition before we can perform the division. This is because, that sounds backwards, but again, fraction bars are grouping symbols. So it's an implied set of parentheses around the bottom. You have to deal with what's in parentheses before you can do the division. This is a really great one for the trick I was showing you up above, clearing fractions in fractions. So again, the way that works is we look at this and say, okay, I have a problem with a 6 over y and a 2 over y. I would like to deal with that. So I find their common denominator, in this case, just a y again, and I'm going to multiply top and bottom of this fraction by that common denominator. The top works out really nicely. 6 over y multiplied by y. Again, if you need the reminder, you can put that y over 1. So we get a 6y over y. The y's cancel basically, and we're left with just a 6. The bottom, you have to remember those implied parentheses. Once again, there has to be a distribute here or you're going to get this very wrong. When I multiply a 2 over y by a y, the y's cancel and I'm just left with a 2. Nobody usually forgets that. The one people forget is that the 4 also has to get multiplied by the y. If you don't remember to do that, you're going to lose your variables completely. So if you're ever working on one of these and you've lost your variables, check and see if you missed a distribute. I actually think I can do a little bit better here. Right now the bottom is written as a sum, so I can't cancel anything, but I could factor a 2 out of the bottom and then cancel. So I'm going to make the bottom 2 times 1 plus 2y. The top is 6. Now I can split this up and say, okay, the top is a 3 times 2, so I'll cancel the 2, and I'm left with a 3. And my answer here is a 3 over 1 plus 2y. So do simplify when you can. Reducing fractions is always good simplify. You should always get rid of fractions and fractions. You should always deal with negative exponents. I don't need you to factor things unless you think you're going to be able to cancel. I do not want you, once again, to make an extra step here and assume this thing equals 0 and solve. There's nothing in this that says you should be solving for y. This problem just asked you to plug a 2 over y into a specific function and say what you get. So we are completely done with this. Okay, have a couple more evaluates and then we'll do a solve. So let's see, I'm just going to cover this up so we can see our original function again. Maybe. There we go. Okay. Let's find g of y squared. And just so you can see where I'm going with this, I want to compare that to finding a g of y squared. So this is that input versus output thing. It's really important that you're clear on when you're messing with your input versus your output. So this first one, you always want to work your way from the inside out with parentheses. So we're supposed to start with a y, plug it into function g, and then square our output. So this says plug y into g. You should get 3y over y plus 4. That's the g of y. And then we're supposed to square that entire thing. So that's really it. I think I would take the step here, get rid of parentheses. It's fairly easy to do. So on the top, I'm going to get a 9y squared. And on the bottom, I'll get a y plus 4 squared. I would say splitting up the fraction top and bottom is really nice, although I probably wouldn't talk you here for not doing it. I don't really see a great reason for me to multiply the bottom out. It's nice when you're working with fractions to have things in factored form, so I'm really okay with this. So I do think it's nice to deal with a big set of parentheses. And again, if you're ever in doubt about when you can stop simplifying, just come up and ask me something like that during a test. I'm happy to clarify things like that. Okay, so that's the first one. Again, if you want to multiply out the bottom, that's fine. Make sure you're clear on the fact that there's a FOIL involved in that. That's y plus 4 times y plus 4. So it will not just be y squared plus 16. It'll be y squared plus 8y plus 16. So if we want to compare this to the second one is saying input a y squared into function g. So this is messing with our input, not our output. Function g is going to take our input, y squared, and multiply it by 3. And that will be the top of our fraction. The bottom of our fraction will be our input plus 4. And I don't see anything else that I think needs to happen here. If the bottom was factorable, you could try factoring and canceling. It's not factorable here, so we're set. Anytime you have a perfect square plus something, you're not going to get any nice factors. That's going to be prime. Okay, let's do one last really messy one here, and then a solve, and then we're done with this one. So let's find a difference quotient. I did g of y plus z minus g of y all divided by z. So again, I've said it, this is a difference quotient. Once again, I would emphasize, I think I actually want to see that for a little bit longer, that a difference quotient should stand out to you as some sort of a slope. I don't need you to get really into it, but what I see here is an output minus an output. So that's a rise. We're not going to say y value here because we're actually using y for inputs. The top is definitely a rise. No doubt that the top is a rise. When you take one output and you subtract another output, you get a rise. The question then becomes, if the bottom is the appropriate run, then we have an average rate of change or a slope. So is the bottom the appropriate run? And if we look at our inputs, we have a y plus z and a y. And when we subtract y plus z minus y, we do get z. So that is the appropriate run. So again, function notation is powerful because when you write down a rise, you can immediately see the run that goes with it. So that's kind of part of what we like about it. Okay, so once again with these, this has got a few steps to it. There's two different things that we need to plug into function g, and then we're going to take the outputs that we get and subtract them and then divide by z. So step number one, feel free to do side work if you want to do side work here. I'm going to do it all within one big messy fraction. Step number one is to plug y plus z into our function. Our function is going to build a fraction, and in the top it's going to put a 3 times y plus z, 3 times our input, and on the bottom it's going to put a y plus z plus 4. Again, if in doubt, put parentheses around your input. Here, we do need them on the top. We don't actually need them on the bottom. There's no reason to separate the addition of y plus z from the addition of 4. We are also supposed to plug in a plain old y, and that's a nice easy one. The function clearly tells us that if we just plug in y, we get 3y over y plus 4. So this is the first piece, this is the second piece. We are supposed to find the difference between those two outputs and then divide it by z. Okay, so again, part of this is some recognition of what function notation is asking, and part of this is getting good at some really messy algebra. So I'm going to do one quick rewrite step, and then we're going to see if we can work at dealing with all the fractions and fractions. So the very first piece, I see a distribute that can happen in the top. I have a 3y plus 3z. There's not really anything to be done in the bottom, but I can drop the parentheses at this point. I have a y plus z plus 4. I can't combine any of those, but there's no reason that the y plus z need to be added together before the 4. It makes no difference when you're adding what order you do that in. All right, and then we have a minus 3y over y plus 4 divided by z. So again, I'm really deliberately trying to show you this clear the fractions and fractions algebra trick repeatedly so that you get used to it and good at it, and that's definitely what I would use here. I want to clear fractions and fractions. So I'm going to multiply top and bottom of this big fraction by the LCD. This time the two fractions that I'm worried about are in the top. These are the two denominators that I would like to cancel out. So my LCD is going to be the combination of those two. Neither one of those is going to factor anymore for me. And you want to make sure that you're really clear on the fact that the first one having a y plus 4 and the second one having a y plus 4 doesn't help us at all because y plus 4 is not a factor of the first one. Y and 4 are terms of the first one, but it's all about factors. Since these won't factor anymore, we're looking at a 1 times y plus z plus 4 and a 1 times y plus 4. So we don't need to list the 1. Something's always going to have a factor of 1. That's something we can take for granted, but we do need to make sure we have a y plus z plus 4 and a y plus 4. We can't just go multiplying the top of the fraction by something. We have to do it to the bottom as well. So again, this is a really big algebra trick for us. If you want to change the appearance of something without changing its value, you can multiply it by 1, and you can make 1 look as ugly as you would like to. But basically, as long as the top and the bottom of your fraction are the same, you really are just multiplying by 1. This time, the one we're going to want to be really careful with is the top. There's a subtraction in the top, so we will have to distribute. So I actually think I'm going to write the bottom out first. Nothing very big happens in the bottom. We're multiplying z by y plus z plus 4 by y plus 4. There's no cancellation. There's no fraction. So basically what we're doing in this step is moving all of this extra mess to the bottom. Might seem like a terrible plan, but it actually is helpful. So when you have fractions and fractions, moving some of that extra denominator mess to the bottom can help. All right, so on the top, We have to remember this distribute. So when we perform, let me cover this one up. The first multiplication, we're multiplying the 3y plus 3z over y plus z plus 4 by our LCD. What will happen is the y plus z plus 4's will cancel. Again, if you need the reminder, you can put this whole thing over 1 and this whole thing over 1. This is multiplying into the top of the fraction. So y plus z plus 4 will cancel. We will be left with a 3y plus 3z from the top of the fraction and a y plus 4 from the LCD. So it's messy, but there's no longer a fraction. So I would still say it's an improvement. The minus sign is just going to carry through. And now we want to multiply the second fraction by the LCD. So when we perform this multiplication, the y plus 4's will cancel. We'll be left with the 3y from the top of the fraction and the y plus z plus 4 from the bottom of the, or from the LCD. I'm sorry, not from the bottom of the fraction. Okay, so this might look horrible. Sometimes they do look horrible for a step or two, but I still would say this is an improvement. We no longer have fractions in fractions, and that's a good thing. The next thing we'd like to do, generally with difference quotients, you're trying to simplify until you can cancel out whatever you started with in the bottom. So canceling out a z would be really great here. I don't want to mess with the denominator at all because it's already in a factored form. This is all multiplication. So if I could get the top factored, I would be free to try and cancel out z's, y plus z plus 4's, or y plus 4's. The top is a big old ugly difference. So it is not written as a product yet. It's not factored. We will try and fix that by multiplying everything out on the top and seeing if we can clean it up a little, seeing if anything drops out for us, and then trying to factor it. Okay, so I see a FOIL. There's a 3y squared plus 12y plus 3yz plus 12z. And I said 12y and I did not write it. Make sure I didn't lose anybody else. I don't think so. For the second chunk, we want to distribute and make sure the minus sign is part of that. So we're going to pick up the negative 3y and we're going to distribute it to the y, the z, and the 4, which means we'll get a negative 3y squared, a negative 3yz, and a negative 12y. Barely fit that in. Over a big mess in the bottom. Okay. So checking out what's going on in the top, I have some terms canceling out. So I see that there's a 3y squared here and a negative 3y squared here, which means when I add those up, I will be left with 0. I can wipe them out completely. I also see a 3yz and a negative 3yz. Those will wipe each other out. So again, trying to be really clear here, that is not a division. I'm just adding or subtracting terms and ending up with 0. So cross them out completely because 0 is left over. Last one, I have a 12y and a minus 12y. So those as well will add up to 0, which means really all I have left here is a 12z divided by z times y plus 4, y plus z plus 4. We'll go ahead and flip-flop the order there, times y plus 4. I can finally cancel out that z. So I have a y plus z plus 4 times y plus 4 on the bottom and a 12 on the top. And I don't see that I'm going to be able to do any better. There is no reason to multiply out that denominator. Once you've got something in factored form, if you're working with fractions, it's wonderful. Keep it that way. The reason, one more time, that we multiplied this one out is because it was not, the whole thing was not in factored form. Individual terms were factored, but the big operation here, the last thing happening in the top, was the subtraction. So the big thing was not a factored form. Okay, one last part for this one, and then we'll try something else. Let's see, where is the original function? Let's do one quick solve here. Hopefully we've done our algebra review and we're getting good with the solve, but I like to make sure I remind you of some funny things along the way. So here's one. I could also ask you to solve instead of just evaluating the function at different inputs. Let's try g of y equals 3. So this one actually doesn't look terribly messy, but an interesting thing happens. Once again, you want to be really clear here. I'm not redefining the function. But you can't see the function. There we go. The function is still the one we started with. G of y is 3y over y plus 4. This is saying for what y values, what inputs, will your output of that function be 4? So will your output of that function be 3? Set your output equal to 3. G of y is the same as a 3y over y plus 4. And I would like to know when that will equal 3. This is rational, so let's multiply both sides of the equation by y plus 4. And I see that this left me with a little mess. So the first mess was the fractions. We clear the fractions. This creates a new mess, parentheses. We can deal with that by distributing. So I'll end up with a 3y plus 12. If you'd like to deal with both of those in the same step, that's completely fine with me as long as you're careful. Okay, so something really interesting is happening here. The next thing we should notice is that we have y's on both sides of the equation. So we need to be working to fix that. If I try to move all my y's to either side, so let's say my thought process is I would like to move the y's to the left-hand side. That means I have to move this 3y over. It's attached by addition, so I'll subtract it. Minus 3y minus 3y. And what I get is 0 equals 12. Let me switch colors on you. This is a clearly false statement, and there are no variables left. What this means is no matter what y value you choose, the two sides of these equations are never going to be balanced. They'll never give you the same thing. If you take a number and multiply it by 3, and then you take the number and multiply it by 3 and add 12, there's no possible way that you're going to get the same answer. So this is a no solution. It's not no solution because we solved correctly but got an extraneous solution. It's no solution because it actually isn't even possible to get a candidate for a solution. This equation doesn't lead to any possibilities. So no solution. So there are other ways we can run into no solution. All right, that's it for this long one. Thanks for watching.